11s, in today's video we're going to continue with electromagnetism, and we'll be focusing on the calculations for electromagnetism, namely how to calculate magnetic flux, and we'll also be looking at how to calculate the magnitude of induced EMF. Let's go. As a quick recap, in the previous videos in this playlist, we looked at what electromagnetic induction is, at what magnetic flux is, we discussed the concepts, and we looked at both formulae. If you want the links to those videos, check out the links in the description box below. It's very important that you understand and go through those videos before you watch this one. But as a quick recap, the two formulas you see on the screen, first of all, the one on the right-hand side, this is to calculate magnetic flux. So this symbol is the symbol for magnetic flux, and the unit for magnetic flux is Weber, W-B, Weber, Weber, something like that. B is magnetic flux density. It's basically a measure of how strong the magnetic field is. If you use a stronger magnet, you get a larger value for B, larger magnetic flux density. And the unit for magnetic flux density is Tesla, which is represented by the symbol T, T for Tesla. Then we've got, it's a big capital T. Then we've got A, and that is area. And it's the area of the conductor. So that's the conducting wires, the coil, the loop, whatever it is, and it's measured in meters squared. Then we've got cos of the angle, and remember that the angle is the angle between magnetic field, magnetic flux density, so basically the magnetic field lines, and the normal to the conductor. That is what theta is. Then our formula on the left, that's the formula in order to calculate induced EMF. Remember, induced EMF is the EMF that is created or produced along the ends of the conductor because of a changing magnetic flux, when there's relative motion between the conductor and the magnet. Induced EMF is measured in volts. V, it's a voltage. N is number of turns, and that has to do with the coil or the wire, how many turns are in the coil or the wire, so number of turns. Now, this symbol over here, again, this means change in magnetic flux. And remember, magnetic flux we calculate using this formula. So when we say change in magnetic flux is final magnetic flux minus initial magnetic flux. That's what change means. Change is always going to be a final minus an initial. And then this is time, change in time in seconds. So those are all the variables. Now let's take a look at some questions that will utilize one or maybe both of these formulae. So here's my first question. A circular conductor with a diameter of 70 millimeters is placed in three different positions in a magnetic field with a strength of 0.8 T. Remember, T is Tesla. Calculate the magnetic flux through the conductor if the magnetic field relative to the conductor is as follows. Parallel, perpendicular, and at an angle of 60 degrees. Now, grade 11s, if this angle relative to the conductor is confusing you, you need to go watch my previous video on magnetic flux, where we basically spoke about the conductor. Say it's a circular conductor or a square conductor, and then there's a normal. Okay, the normal is an invisible 90-degree line. So if this is the surface of the conductor, let's pretend it's a circular conductor like this. The normal will be like this. Okay, so the angle has to do with relative to that normal. And it says here, calculate the magnetic flux through the conductor if the magnetic field is as follows. So you can have magnetic field that is parallel to the conductor. You can have magnetic field that is perpendicular to the conductor. Just a quick reminder that the different situations look like this. So our different situations were as follows. If you take a look at the situation on the left-hand side, we have a situation where the magnetic field lines, which are the red-orange lines, they're going down like this, are parallel to the normal. Now remember, the normal is like an invisible line. So the black object on the screen on the left-hand side, that is the conductor. So this over here is the conductor. The normal is like this. Take a look at the field lines. They are parallel to the normal. The field lines are going down like this. So the field lines are parallel to the normal, but the field lines are perpendicular to the conductor because the conductor is like this and the field lines are like this. So just take a look here. This is conductor. This dark box over here is conductor, and this is the field lines. So in this context, the magnetic field is perpendicular to the conductor, but the angle that we use in my formula is actually 0. Because remember, the angle is the angle between the normal and the magnetic field lines. The angle is between the normal is the dotted line, and the magnetic field lines. The angle is 0. However, the situation on the right-hand side, the magnetic field, remember the magnetic field lines are going down. Remember, I'm talking about this situation over here. The magnetic field lines is perpendicular to the normal, but parallel to the conductor. So I hope you can see that the conductor is now on its side. It's rotated like this. The magnetic field is perpendicular to the normal. Remember, the normal is like this, okay, or like this. It's at a 90-degree angle. This is the normal. Yeah. So the magnetic field lines are 90 degrees to the normal, but the magnetic field lines are parallel to the conductor. Take a look at how that picture looks. The magnetic field lines are going down, and the conductor is sitting down like that. I hope that makes sense. It's quite confusing. In that scenario, the angle is 90, because remember, the angle is the angle between the normal and the magnetic field lines. So again, here's the normal, here's the magnetic field lines, the angle is 90. I really hope that makes sense. So in our questions, where our first one says calculate the magnetic flux through the conductor if the magnetic field relative to the conductor is as follows, where the magnetic field is parallel to the conductor, we're considering a situation like this. So the conductor is like this, the magnetic field lines are like this, they're parallel. The angle, however, is 90 because the angle is between the normal and the magnetic field line. So how would you do this? What formula would you use? You're working out magnetic flux, so you would use the following formula. You would use this formula where you go magnetic flux is equal to magnetic flux density multiplied by A multiplied by cos of the angle. Now, B is your magnetic flux density, and that is measured in Tesla. That's that value over there, so it's 0,8. Then the area. They say it's a circular conductor, so the conductor looks like this. Ignore the fact that my picture is a square conductor. It doesn't matter. It's a circular conductor. So now how would you calculate the area of a circular conductor? Well, you would work with the area of a circle. Area is equal to pi times radius squared. Now, diameter is 70 millimeters. The diameter is 70 millimeters. The radius, as you should know, is half of the diameter. Remember, diameter is a line through the center point to the midpoint of the circle, like that. Through the whole circle, the radius is half of that. So we care about radius for my area formula. It's 35 millimeters. We need to convert that to meters. It is 0,035 meters. You need to convert to meters. That's because, remember, we discussed that in this formula, area is measured in meters squared. So it cannot be in millimeters. You need to convert. And to convert from millimeters to meters, you divide by 1,000. Right. So we've got pi times radius. Now remember, the radius is 0,035 squared. That is the area of my circle. And if you work that out, you get 0,0038. You should actually not round that off. So it should be 0,0038485. You shouldn't round it off. Your calculator may give it to you in scientific notation as well, depending on the settings. 3,8485, so on, times 10 to the power of -3. It's the same thing. So whether you write it in like decimal, 0,0038, blah, 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 or 3,8485 times 10 to the -3, it's the same thing. Depends on your calculator settings. We don't round off because we're not at the end of the question. So the area is going to be that number. What I'm going to do is I'm going to leave it on my calculator or store it on my calculator, but I'm not going to round off. Then, cos of the angle, I'm just going to erase this to give myself space. Cos of the angle, now again, grade 11s, the angle that we use is the angle between the normal to the conductor. This is the normal, the dotted line. So take a look at the picture. The normal is the dotted line, that dotted line over there. So it's the angle between the normal and the magnetic field lines. The magnetic field lines are coming down like this. the normal is like this, the angle is 90 degrees. And if you type that into your calculator, what you should get is actually 0. And the reason why is because cos 90 is equal to 0, and 0 multiplied by anything is 0. So 0 Weber. That is the magnetic flux. Now, question number 2 is basically the same question, except now the position of the coil or the conductor has changed in the magnetic field. So note how the magnetic field is still going in the same direction, but now instead of the conductor being straight up like this, instead of the conductor being parallel to the magnetic field, the conductor is perpendicular to the magnetic field. So the conductor is like this. Okay, it's a circular conductor. So technically it's like this, and the magnetic field is like this. And I hope you can see that if this is the scenario, all of the magnetic field lines are actually going through the conductor. It's like an open hole. In this case, what was happening is the conductor is like this. So there's the open hole, and the magnetic field lines are going down like this. Nothing is passing through the conductor when it's in this situation. So the conductor, here's the conductor, is perpendicular to the field. What happens is the angle between the normal, here's the normal, and the magnetic field is 0. So the angle is 0. So how it works is as follows. Same formula, exactly the same formula. We're working up the same thing. My B is the same, 0,8. Same thing. My area is the same. Same area because it's the same conductor, 0,00384 ... I'm saying ... because I'm not running off. But now my angle is 0 because remember, it's the angle between the normal and the field lines, which is 0 in this case. If you work that out on your calculator, you should get, there we go, 3,08 times 10 to the negative 3 Weber. Again, if your calculator gave it to you not in scientific notation, that's okay. Now, if my conductor is at an angle of 60 degrees relative to the normal, this is how it would look. Here's the normal, and here are my field lines like that. So that is essentially what's happening. The formula is the same. So BA cos of theta. My magnetic flux density is the same. My area is the same. That doesn't change. But my angle is now cos 60. If you type that into your calculator, what you get is 1,54 times 10 to the negative 3 Weber. Okay, cool. That's it. Let's jump into our next calculation, which is actually requiring us to work out the magnitude of the induced EMF and then the magnitude of the induced current. So we're actually going to focus on using our second equation, or this one over here, for this sum. Now in this sum, our first question wants the magnitude of the induced EMF. Now if we write that formula out, we can see that magnitude of induced EMF is equal to negative n is number of turns, multiplied by change in magnetic flux divided by change in time. Now, what do we have in the question? We have a square wire coil, and they give me the length of the coil, and they say it's a square. So essentially, it's something like this. All sides are equal. They give me the length is 150 millimeters. So we know we're going to have to work out area. And it has 2,000 turns. So we actually have N. So let's take another color pen. We tick that we have N. The magnetic flux density. Now remember, magnetic flux density, let's use a blue pen. Magnetic flux density is B. Now remember, B is not in this formula. However, B is in this formula. B, A, cos of an angle. The magnetic flux density, B, this value over here, through the center of the coil changes from 0.4 Tesla to 0.2 Tesla in 8 seconds. So another thing that we have is time, 8 seconds. And then they give me resistance. Now, in order to calculate induced EMF, resistance is not necessary. We're going to use that later on. But what I do want you to note is that they give me two values for B, essentially, magnetic flux density. They say it changes from 0.4 Tesla to 0.2 Tesla. Now, if B changes, if magnetic flux density changes, what that means is that magnetic flux will change. And that's no surprise because look at what my formula says. My formula does say change in magnetic flux. And change, as I've mentioned earlier in the video, change in magnetic flux. When something changes, you must always have a final magnetic flux minus an initial magnetic flux. So change is always final minus initial. How would we get the final magnetic flux? We would use the final magnetic flux density. How would we get the initial magnetic flux? We would use the initial magnetic flux density. Magnetic flux changes, which means we need to do this formula twice. Once using the 0.4 Tesla, and that would get us initial magnetic flux, and then another time using the 0.2 Tesla, which would give me the final magnetic flux. And then once we have the final minus the initial, we have the change. And once we have the change, we can work out the EMF. So there's a lot of parts to this question. We must also work out the area because we need area over here. So let's get right to it. The first thing that I need to do is work out the area of my coil or my conductor. It's a square, so that's nice and easy. It's side times side or length times breadth. However, my length and my breadth or my side and my side can't be in millimeters. It has to be in meters. So I first converted it to meters by dividing by 1,000. Right, cool. Now we've got it in meters. We're going to say 0.15 times 0.15. We multiply those together and we get 0.0225 meters squared. And that's good because area must be in meters squared. Now, grade 11s, this is not the end of the question. This is one part of the question. So we're not going to round off here. Leave that entire area. Now, what was the point of calculating area? Remember, we need area in order to calculate magnetic flux because B is magnetic flux density, A is area. So now we've got the area. And then cos of the angle. The angle they mention is 45 degrees. Now, in this sum, the angle does not change. The angle stays 45 degrees. However, as I've mentioned, the magnetic flux density changes. So what we're going to do is we're going to calculate final magnetic flux and we're going to calculate initial magnetic flux. And why do we need both of them? Because the magnetic flux density changes. So we calculate final minus initial, which will allow us to calculate change in magnetic flux, which we use in the EMF formula. So let's calculate final and initial magnetic flux. Calculating initial magnetic flux, we use B. And now if you read the question carefully, it says that magnetic flux density through the coil changes from 0.4 Tesla, implying that it was that initially. So that's my initial 0.4, and it changes to 0.2. So we use the 0.2 when working out final magnetic flux. The area, as we worked out earlier, is 0.0225. Same thing here, the area is 0.0225. Now the angle in both cases stays 45. This is cos 45. All we do now is we work that out on our calculator. Remember not to round off. Now take note how I've written the answer both in scientific notation and in normal decimal form. Same thing here in scientific notation and in normal decimal form. Again, it depends on how your calculator gives it to you. Mine actually gave it to me in scientific notation, but on my other calculator, I get it in decimal form. You can change the mode on your calculator to give you either. It doesn't matter what you write it in as long as you don't round it off yet. So keep it to at least 5-6 decimal places to be safe. Your unit is Weber, WB. That's not the final answer. That's the initial magnetic flux that we got using the initial magnetic flux density, and that's the final magnetic flux that we got using the final magnetic flux density. Now I need to work out the change in magnetic flux, which is my final, this one over here, minus my initial. So if you do final minus initial, remember it's always final minus initial, you actually end up getting a negative. That's okay. Let's continue. Substitute it into my formula. So I'm going to write my formula first over here. It's negative n multiplied by change in magnetic flux divided by change in time. Then we're going to substitute in. Number of turns is 2,000. So it's negative 2,000. At the top of the fraction, change in magnetic flux is this number. Remember, Don't round off. So you use that whole number. Changing magnetic flux, negative 0,0031819 ... and it takes 0,8 seconds. You type all of that into your calculator and you should get your change in magnetic flux, which should be, I get 7,95 volts. It's very, very important not to round off, because if you do round off, you might get a slightly different answer. Now, my next question is calculate the magnitude of the induced current. Now, what we just calculated over here was the magnitude of my induced EMF, which is the voltage. Now, remember in the question, they gave me resistance. Once you have resistance and you have induced EMF or voltage, we can easily get current. And remember how we do that is by using our Ohm's law formula, which is basically, in this case, we're going to go I is equal to V over R. We want magnitude of induced current. Induced just means the current that's produced. So we take our answer, 7,95, we divide it by the resistance, which is 4, that's given to us over here, and we get 1,9875 amperes. And because this is physical sciences, you may round off to 2 decimal places, 1,99, you chop it off there, 1,99 amperes. And that's basically how you tackle electromagnetic calculations. They can ask you to calculate magnetic flux, changing magnetic flux, or EMF, or even induced current. I hope that this has been helpful. Let me know down below in the comments what other videos you want to see, and I hope to see you in the very next video. Bye, everybody.